What is going on, guys? Welcome back. In this video today, we're going to learn about RSA, which is an algorithm for asymmetric encryption. We're going to cover it from scratch. We're going to learn all of the mathematics behind it, and then we're going to implement it from scratch in core Python. So let us get right into it. Alright, so we're going to talk about RSA in this video today, which is an algorithm, or maybe I should say a crypto system for asymmetric encryption, meaning we have a public key and a private key instead of one and the same key that we use for encryption and for decryption. So we have two different keys with two different purposes. However, for this video today, you don't need to understand anything about cryptography already. You don't need to know anything about private keys, public keys, signatures, anything like that. I'm going to explain everything from scratch. The only thing that you should probably feel comfortable working with is the modulo operation, prime numbers, greatest common denominators, and understanding what it means for two numbers to be co-prime. So very basic mathematics, knowing what a prime is, knowing what it means for two numbers to be co-prime or relatively prime, knowing what the modulo operation is. So what does it mean for a number to be congruent to 2 modulo 15, for example? What does that mean? And also understanding what it means to have a greatest common denominator of 1, 2, 3, whatever. Understanding these basic mathematical things is all you need for this video today. I'm going to explain everything else from scratch. I'm going to keep it simple and intuitive, but I'm also going to give you the exact formulas. And then we're going to take all that theory and we're going to put it into Python code to see that this actually works to encrypt a message like hello world, for example. So let's get started with the intuition behind using public and private keys. Without talking about RSA yet, without talking about anything specific mathematically, we're just going to look at what it means to use a public key and a private key. The basic idea is, and this is the example that you will find everywhere, is we have Alice and we have Bob, and Alice and Bob want to exchange a message or multiple messages. So Alice wants to send a message to Bob, the message M, but she doesn't want this message to be in clear text. She doesn't want anyone who is listening here, for example, Eve, she doesn't want Eve to listen to that message and see what's written in that message. So we want to somehow encrypt the message in a way that only Bob can know what the message actually says, and Alice, of course. So what Alice would do is she would encrypt that message in some way. Let's say we have a function E that encrypts that message, and this would produce a ciphertext, so something that's unreadable, unusable to anyone who reads this. However, Bob would then have some way of using decryption, another function D, for example, on the ciphertext to get M back as a result, to get the message. So that's just encryption in general. That's not asymmetric encryption. This is just encryption. Now, how you do that? You can do that in a symmetric way, and you can do that in an asymmetric way. A symmetric way would be for Alice and Bob to somehow have a shared secret key. Let's call this key K, for example. They both have the same key K, and Alice can use now to encrypt the message M this key K. So we could have a function E, which puts in K and M, or M and K, whatever, and we get some ciphertext, and Bob can then use the same key to decrypt the message, actually not the message, the ciphertext into the message. That would be symmetric encryption. This is not what we're talking about today, because today we're talking about asymmetric encryption, RSA. And what we do with RSA, or what we do with public-private key encryption, with symmetric encryption in general, is that we generate a key pair, a so-called public key and private key, a key pair consisting of those two keys for everyone. So Bob would have a private key and a public key. Let's call this pub and priv, not private key, like this. Or also the private key is oftentimes referred to as secret key, and Alice would have her own public key and her own private key. So the idea now is that we keep the private key secret. So our assumption is Bob is the only person on the planet who knows his private key. Alice is the only person on the planet who knows her private key. But the public key, with the public key, you can do whatever you want. You can upload it to the internet. You can publish it anywhere. It doesn't matter. Everyone can know your public key. And the basic idea now is that when Alice wants to send a message that only Bob shall read, what she does is she encrypts the message with the public key of Bob. So basically, We have the message M, or maybe let's keep it consistent. Let's first provide the key. We have the public key. Let's call it pub B for Bob. We're passing the public key of Bob into that function, and we encrypt the message to get the ciphertext. Now, the keys are constructed in a way that when Bob now uses a decryption function to decrypt the cipher in order to get message M, what he has to pass into this decryption function is his private key. So private key Bob. So we don't pass the same key into the function to decrypt the message, but we just pass the corresponding private key. The only way to decrypt a message that was encrypted with Bob's public key is to use Bob's private key. And the other way around, if Bob now sends a message to Alice, he will encrypt the message with Alice's public key, and she will have to decrypt the message with the private key. That is the general high-level explanation of what is happening. How this is done exactly mathematically is what we're going to talk about next. But this is something that you need to understand here. For those of you who have never heard of this, everyone generates their own key pair. We're going to talk about exactly what that means, generating the key pair, finding the corresponding key and all that. We're going to talk about this. But for now, just understand there are two keys for each person, public and private. When you encrypt something with the public key, you decrypt it with the respective private key. And also, as an additional thing that you can do is you can also do it the other way around. Let's say, for example, we don't want to encrypt or decrypt. What we want to do is we want to send a clear text message to Bob, but we want to make sure that Bob knows this comes from Alice. What Alice can do is Alice can send a so-called signature. And a signature basically means Alice uses her private key that only she knows to sign the message M. So we could say sign the message M to get some signature S or whatever. And she can pass it with the message. So she can send to Bob the message, whatever, hello or something. And so that Bob knows that this is actually coming from Alice, she also sends a signature. And in order to verify that signature so that Bob can actually find out, okay, Alice sent this message and this signature is correct or valid, Bob just has to verify the signature with Alice's public key. So to summarize it one more time, if Alice wants to send something to Bob that only Bob can read, she encrypts it with his public key. He has to decrypt it with his private key. If Alice wants to sign something for Bob, she signs it with the private key, and Bob can verify it with her public key. That's the basic idea. And now we're going to talk about what exactly this means. So how do we come up with a public key? How do we come up with a private key? What is happening in RSA? And everything in RSA has to do with prime numbers. So what you do in RSA to generate a key is you first have to use very large prime numbers. Now, for this example today, to help you understand what's happening, we're going to use very small prime numbers. So we're going to use something that's manageable for us. We're not going to generate massively large prime numbers because we want to follow the process with our brain, which is limited, and we don't want to have a 100-digit prime number here. So the first thing that you want to do, let's say we're Alice now, we want to generate everything for Alice now. The first thing we want to do is we want to find two prime numbers, P and Q, which are, again, large prime numbers in reality. Now we're going to use quite small numbers, and we want to get their product, so P times Q. For example, P can be 11, and Q could be 13. So if we have 11 and 13, if we multiply those two together, this will result in a number n. N would be 11 times 13, so n would be 143. So just so I make this clear here, those are in reality massive, huge prime numbers. It's important that they're prime. Prime, again, means not divisible by any number other than themselves and 1. So those are large prime numbers, and this is the product of two large prime numbers. In this case, 143. So what we do next is we calculate something called Euler's Taussian function. So this is a function called phi, and it sounds more complicated than it is. It's quite simple. What this function does is it just tells us how many values, how many numbers are there lower or actually smaller than n that are co-prime to n. So if we have now 143 here, 143 here, we would go through all the numbers 1, 2, 3, 4, 5, and so on up until 142. And we would ask how many of those numbers are co-prime to 143. So basically meaning they have no, basically that means we have the greatest common denominator of 143 and the number that we're talking about, x, is 1. So there's nothing that divides both numbers other than 1. That means co-prime. And of course, what we could do now is we could just check for each number, okay, this is co-prime, this is co-prime, this isn't co-prime, and so on and so forth. We could just then count the numbers, but that's a very tedious process, and that's not really what you want to do, and this is not something that is possible when you have huge prime numbers. This is just not reasonable to do that. It doesn't work. But what we can do is we can use a formula, and the formula basically says that phi of a prime number, and this is something that you don't even need a formula for, you can just think about this. If you have an actual prime number, if you have a number that's prime, it's not divisible by anything other than itself and 1. What is going to be phi of n? It's going to be, of course, every number below it. So if I have the prime number 11, for example, every value below 11 is going to be co-prime to 11 because 11 is prime. There is no number that divides 11 other than 1 and 11 itself. So every number below 11 will be co-prime to 11 because 11 is not divisible by anything in the first place. So actually, if you have a prime number, the formula is just n minus 1. So for 17, you have 16 co-prime numbers below 17. For 13, you have 12 co-prime numbers below 13. For 11, you have 10 below 11, and so on. So that's very obvious that this is the case. Every number below a prime number is co-prime to the prime number, obviously. Now we have another, and maybe I shouldn't use n here, sorry. So this is this was a general statement. Phi of x, you could say, is x minus 1 if x is prime. That's what I was saying. Now, n is not prime. N is the product of two prime numbers. By definition, n is divisible by p and n is divisible by q, so it cannot be prime. However, there is a nice thing that we can do here. Phi of n is basically just the product of phi of p times q. And this is the same thing as saying phi of p times phi of q. And that basically just means that that is p minus 1, because p is prime, times q minus 1, because q is prime. And now all this tedious work of checking all the numbers is gone, because all I have to do now to calculate phi of n, which again, maybe let me write this down here, is Euler's Taussian, I hope I pronounce this correctly, function. All we have to do to calculate this value here is we need to subtract 1 from p, subtract 1 from q, and get the product. That's quite simple. It's 10 times 12, because we have 11 and 13. 11 minus 1 is 10. 13 minus 1 is 12. 10 times 12 is 120. That is our phi of n. Now, it's important to know now what exactly are we keeping secret here, because we haven't generated any private or public key yet. This is just some setup work here. You never want to tell anyone p, you never want to tell anyone q, and you never want to tell anyone phi of n. N can be public. N is going to have to be public because we're going to use it. But p, q, and phi of n are going to stay secret, because if you know these values, it's very easy to also just crack all the other values. So phi of n is very difficult to find, because you would have to just go through all the combinations if you don't know what p and q are. If you know what p and q are and you know there are two prime numbers, you just use this formula here, quite simple. If you don't know it, it's very tedious. It's not reasonable to expect that you're going to find out what phi of n is. But phi of n is super important, because phi of n is what we're going to use now to actually determine the private key. Because what we want to do, public key, sorry. What we want to do to generate the public key is, and we're going to call our public key E, for encryption, for example. In order to find E, what we need to do is we need to just pick an integer that is basically that is congruent, or actually not congruent, sorry, that is less than phi of n, sorry for the brain lag now, less than phi of n, larger than 2, and where the greatest common denominator of e and phi of n is 1. Meaning, in other words, again, coprime to phi of n. So this just means coprime or relatively prime. So to summarize it again, without a brain lag this time, e has to be between 2 and phi of n, not including 2 and phi of n, and it has to be coprime to phi of n, meaning that the number e that we pick doesn't have anything that divides it that also divides phi of n. So there are multiple answers to that usually, but what you can do here, for example, is you can just go with 7. So you can try different combinations. It's not too difficult to find something that works. 7 itself is a prime number, so whenever e is a prime number, you can just check if this number is divisible by 7. In this case, it's not, so they're coprime, because we don't have to check for anything else. If phi of n is not divisible by the prime number that you choose for e, then then there's not going to be anything else. All right, so I'm going to remove all of this here again. E is 7. 7 is less than 120, it's larger than 2, and it's coprime to 120. So this now is our public key. Again, we're working with very small numbers. Usually this number is going to be quite large. Now it's just 7. So 7 is our public key. Now, the magic comes here now with the generation or the determination of the private key. So since this is the public key, we now need a corresponding public key. We now need a corresponding private key. And how we find this private key is by saying it has to fulfill the following rule. E times D, this is going to be our private key. Private key. The following relation has to be true. This is the multiplicative inverse, meaning if I multiply E times D, the result is congruent to 1 modulo phi of n. What this means in clear text is that when I multiply these two numbers, whatever they are, this public and private key, I get a remainder of 1 if I was to divide by phi of n. So for those of you who don't know what modulo is or don't have an intuition for modulo because it has been some time, if I say 10 divided by 5, that is 2 with 0 remainder. Okay, so that means 0 remainder. This would mean that that 10 is 0 congruent to 0 modulo 5, because I can divide 10 by 5 and I get 0 as a remainder. 11, if I divide 11 by 5, it would have 2 as an integer result and then a remainder of 1. So 11 would be 1 modulo 5. And it would also be 1 modulo 10. And it would also be 1 modulo, would it be 1 modulo something else? I'm not sure. Yeah, it would be 1 modulo 2 as well, because 2 times 5 is 10, and then, yeah. And this is just a rule that we want to have here. We want to have a number D that when I multiply my public key E with that number D, the remainder of a division by phi would equal 1. And phi in our case is, remember, 120. So essentially what I'm looking for is 7 times something, which is D, is congruent to 1 modulo 120. Or again, in other words, I'm trying to repeat it as much as possible so that it sticks in your brain and it's quite simple to understand. If I take 120 and divide it by 7 times D, whatever that is, not 7 times 9, 7 times D, whatever D is, the remainder of that division would be 1. That is what I'm looking for. Now, how do you exactly find that? To do it automatically and professionally, you would use the extended Euclidean algorithm, which I don't want to go into right now. For small numbers like this, you can just brute force. You can just go through all the combinations and see if that's true, because you just go 7 times 1, 7 times 2, 7 times 3, and so on. And at some point, you get to a number. In our case now, this number would be 103, because 7 times 103 is 721. You can also calculate now 120 times 6. That would be exactly 720. You can see there's a 1, there's a 0, a remainder of 1. Basically, this is congruent to 1 modulo 120. The only thing that you need to understand here now is, of course, we just can go through the numbers and check, and we will come up with the answer. Just understand, for computers, this is super easy to find out. If you know 7, if you know 120, you can easily find D. The secret here, and the reason why it's difficult for someone who doesn't know anything, is they don't know what phi of n is. They don't know 120. They don't know anything about phi. They know what n is, but you cannot just find phi of n if you know n. You need to know p and q. It's ridiculously hard to find out what p and q are based on n. There's nothing right now, as of this point in time, that allows us to find p and q efficiently if we just know n. And thus we can also not really calculate phi of n efficiently, and thus we don't even know what the condition is. It's not that it's hard to find out what d is when you have this condition. It's just that you don't know what the condition is in the first place. You're looking for 7 times d is congruent to 1 modulo something that depends on n, but you don't know what that something is. So it's basically impossible for someone to find out what d is based on n and e, because they don't have phi of n. So the only thing, again, I'll repeat, what you need to understand here is this calculation is easy if phi of n is known. But someone who doesn't generate this key pair, they don't know p, they don't know q, they don't know phi of n, and they cannot find out phi of n. So basically now what we have here is we have e equals 7, we have d equals 103, and again, those are large if you do this in real life. If you don't do this here as an example. And this is just the public key, and this is just the private key. There you go. So this is the generation. Now you have a public key and a private key, and Bob would now do the same thing. So this is for Alice. Remember, this is for Alice. Alice now has E equals 7, D equals 103. Bob would do the same thing, of course, with different prime numbers. He would not use 11 and 13, but maybe 7 and 17 or something like that, some other prime numbers. And of course, again, those are also large. He would calculate his own phi of n. He would calculate his own private and public key. And then Bob also has such a key pair. Now, how do we actually use these keys to encrypt and decrypt something? And to explain that, I'm just going to use, again, let me just re-sketch Alice and Bob down here. I don't want to use the example from, or I don't want to use the sketch from above because there's so much stuff here. So we're going to continue down here. Alice and Bob are going to communicate now. Alice has a public key of 7 and a private key of 103. And she wants to send a message M to Bob. And let's say this message M is, we're also going to use a number. I'm going to show you how we can also encrypt text, but text is essentially just numbers because a character is just ASCII code or Unicode code, whatever. But we're going to just have a very simple message for Bob, and the message for Bob is going to be 15. So 15 could be a character, 15 could be a code. 15 is just a number that we want to transmit to Bob, but we don't want Eve to find out that the message is 15. So what would we do? Or actually, sorry, we would want to do this the other way around. Bob wants to send Alice a message because Alice now has this key pair and we don't want to do the same thing for Bob. So again, Bob wants to send a message to Alice. The message is 15. Bob knows that Alice's public key is 7. So what Bob does is now he applies a formula for encryption. And the formula for encryption is that the ciphertext C is the result of taking the message M, which is 15 in our case, and taking it to the power of E, which is the public key. And of course, one thing that Bob also knows is Bob also knows, since we said it's not private, it can be shared with everybody. Bob also knows N, which in our case was 143. This is also public information. Bob knows 143, so Bob is going to also say modulo N, meaning Bob says 15 to the power of 7 modulo 143. That is the calculation that Bob uses to get the ciphertext. And now we can just use a calculator to figure out what the result is. So 15 to the power of 7 and then modulo 143. That is 115. That would be the ciphertext that Bob sends to Alice. So Bob actually sends to Alice the ciphertext 115 or 115. And again, this would look differently because N would be larger, C would be larger, everything would be larger. Now, what Alice does is Alice takes this ciphertext, and in order to get the message, the original message of Bob, what Alice does is she takes C to the power of the multiplicative inverse of E. What is that? The private key D. C to the power of D reverses the operation of M to the power of E. This is how we chose D. This is the condition that we chose up here. We wanted D to be the inverse of E. So now when you multiply or when you take something to the power of E, taking the result to the power of D reverses the operation. And again, modulo N. So in our case, in order to get this, we say 115 to the power of 103 modulo 143. Let's go to the calculator again. 115 to the power of, what did we say? 103 modulo 143. There you go. 15 is the result. So M is 15. Now, for the signature, it's just the other way around. So if we don't want to transmit an encrypted message, we just want to sign a message, what we would do is we would do it the other way around. So what Alice would do is she would say, okay, Bob, I have a message for you and a signature for you. The message would be, again, let's say 15. So we can also just pass the clear text message. It doesn't have to be secret, but Bob shall know that this is not a message coming from Eve faking to be Alice. So this is not a fake message. This is actually Alice. So what Alice does is she generates a signature by saying message to the power of the private key only I know modulo N. So in this case, again, the message is 15 to the power of 103 modulo 143. So again, let's put this into the calculator. 15 to the power of 103 modulo 143 141. So the signature would be 141 and or basically just S here. And Bob now, what Bob would do is he would read the message, says 15. Great. Thank you, Alice, for the information 15. I want to know that this is actually what you sent me. So what I'm going to do is I'm going to verify this by saying I'm going to take the signature to the power of your public key, because the only way something is verifiable is if you is verifiable with your public key is if you encrypted it with your, or if you signed it, sorry, with your private key. So I'm going to take your signature to the power of your public key modulo N. And if this basically results now in the same message, I know it's authentic and I know it's what you sent me. So I'm going to just say 141 to the power of 7 modulo 143. And that to the power of 7 modulo 143. 15. Okay, seems like this is what you actually sent me. So now I have the message and I also know it's from you. That is the theory behind RSA. This is how it works. This is the mathematics. And now we're going to put all of this into core Python code. All right, so now we're going to take all of this theory and all of the math and we're going to put it into Python code. We're going to start by generating two prime numbers. We're then going to calculate their product, which is going to be n. We're going to determine phi of n, and we're going to find an e that is co-prime to phi of n. And we're going to find also the corresponding d, which is the multiplicative inverse. And then we're going to use the public and private key for encryption and decryption. So we're going to start here by importing random, which we're going to use for the generation so that we don't have to use static prime numbers. And then we're going to use a helper function, is prime, which is just going to check if a number is prime. And we're going to say if the number is less than 2, it's automatically not a prime because those are not considered prime numbers. Otherwise, we're going to have to use a loop, or actually we don't need an else statement. We can just say for I in range 2 up until basically half of the number plus 1. So basically we can say number divided by 2 plus 1. And if any number here divides, or if the number divided by I, whatever I is, results in a remainder of 0, then it's not a prime number because it's divisible by I. So we're going to say return false. And if nothing happens, if we don't find a single number at the end, we return true. That is the basic idea of this function. Then we're going to use a generate prime function here, which is also going to be just a helper, min value, max value. And what we want to do is we just want to say prime is going to be a random random integer between min value and max value. And while not is prime, we're going to just generate another one. So basically we're going to copy this here. Probably not the most efficient way to do this. I don't know, maybe there's a more efficient way. We could also just use a static list, but especially when you get to large prime numbers, you probably have an algorithm that does something that's smarter than just going through the values and generating numbers and numbers and numbers until we find something that's prime. But in this case, we're just going to do it like that. It's good enough for what we're trying to do. And we're going to return that prime number once we have it. And what we want to do then also is we want to import math because we want to use the greatest common denominator function. And then we're going to have, I think, one final function, which is going to be determine the mod inverse, so multiplicative inverse. We're going to pass e later on and phi, and we're just going to try to find d with this function. So for d in range not 2, so we're going to start with 3 up until phi. Phi is not going to be included. What we're trying to do is we're trying to say if d times e modulo phi is congruent, or if d times e is congruent 1 modulo phi, so if the remainder of a division by phi is 1, then we return d because we found this number. Otherwise, we're going to raise a value error. Mod inverse does not exist, or something like this. Not going to happen, so we're going to just do it like this. Or actually, if it's not going to happen, we can also just ignore this. There you go. No, I'm going to leave it in there just in case we need to be notified. I don't want the script to crash, and I don't know why. So I'm going to just leave it there. Those are the functions that we're going to use, and now we're going to just follow the same process that we followed in here. So remember, the first thing that we did here was generating two large prime numbers and getting the product, which is n. So we're going to say now p and q are going to be generate prime from, let's say, 1,000 up until 5,000. Still not large prime numbers, but a little bit larger than what we had before. So something like this. And then we're going to say while p, in the case that p is the same as q, which could happen, of course, we want to regenerate q. So q is going to be generate prime, 1,000, 5,000 is the range. Basically just meaning we're generating two prime numbers in case they are the same prime number. We're just going to regenerate it until they're no longer the same. And then we want to calculate n, which is just p times q. And for the totient function now, for phi, we're just going to calculate p minus 1 times q minus 1. We don't need to look for anything because we already know that those are two prime numbers, and we know also what these two prime numbers are. So phi of n is just going to be p minus 1 times q minus 1. And then all we need to do here is we need to say e equals random dot rand int. We're going to start with 3 and phi of n minus 1. And then we're going to say while math dot greatest common denominator GCD of E and phi of n is not equal to 1. So as long as they're not coprime, we're going to just generate another E. So just to associate this with this here, we already have n, we have p, we have q, we have phi of n, which we just determined with this formula here. And now what we're doing for E is we're just trying to find an E that is between 2 and phi of n, not including 2, not including phi of n. So basically from 3 to phi of n minus 1. And we want a coprime E. So probably it would make more sense to iterate. I'm not sure. Maybe if you have large numbers, it's more efficient to just do it randomly. Not sure. But we're going to do it like this now. It works. And then all we need to do finally to get the private key is we need to say D equals mod inverse of E and phi of n to generate the private key, which is exactly what we did here. And in our case, as I said, since we're not working with massively large numbers, this is just an iteration approach. There is a more sophisticated algorithm, as I mentioned, the extended Euclidean algorithm, that does this better. So now we have E, we have D, and we have N. So what we do is we encrypt a message with E. So what we can do is message equals hello world. And maybe just for the information, we're going to print public key is E, private key is D, then N is whatever N is, phi of N is phi N, and of course phi of N has to be kept secret, but we're going to just print it here. And just for our information so that we can analyze this, P is going to be P and Q is going to be Q. There you go. So what we want to do to encrypt the message is we want to take the ASCII code, so basically the ordinal character code of that respective character. So we say message encoded, which is not the same as encrypted. We're just encoding the message. We take the ORT, we apply the ORT function onto a character C for every character C in the message, meaning it's now represented using ASCII characters. Nothing was encrypted yet. This encoded message now, we turn it into a ciphertext. Remember, what do we do for encryption? Where did I do this? I actually deleted it. But for encryption, remember, we said we do message to the power of public key modulo n. So let me just put this here as a comment. M to the power of public key modulo, or actually all of this here, modulo n is the ciphertext. So the ciphertext, we're going to do it here on a per character basis. Now, what you need to understand about asymmetric encryption is you don't use this usually to chat with people. You use symmetric encryption to chat with people. You use asymmetric encryption to exchange keys, to do some small stuff. So you don't apply this on a 500-page PDF document or something like this. However, we're going to do it now here just on a per character basis. So we're going to use the POW function. We're going to say character, public key, and n for character in message encoded. What does this mean? What does the POW function do? Essentially, using POW x, y, or let me just use CEN. Using POW CEN is equivalent to saying character to the power of E and the result modulo n. So that's just C to the power of E modulo n is what this function does. So we do that, and then what we do is we can print that ciphertext, which is just going to be a list now. We can also, of course, join it into a string if you want to. You can also put it into a file, it doesn't matter. But this is now unreadable to us. If I run this here, you can see I have this private key, this public key, this is n, this is phi of n, this is p and q, those are the two prime numbers that we use to create n, and this is the message. Those are just numbers. I don't know. You cannot turn this back into clear text representation. Now, if you were using something that's not as large as these numbers. So if we were working with a limit of, I don't know, 100 here, we would be able to somehow turn it back into ASCII codes or something, but it doesn't make sense because those don't represent anything. So this is now our text. And what we can do now to decrypt it, remember, is we just do the same thing with the private key. So we don't have to divide or anything. We can just use the same function, but we do it with a private key. So what we do is we say, again, message encoded is we take the message that we have, we take the ciphertext that we have, and we take it to the power of D instead of E. So we say pow ciphertext, character in this case. I mean, the C here is for character. Maybe let me change this to not confuse you. This is CH for character. This is not ciphertext. The C from before is the ciphertext. So this is just a character here, a character of the ciphertext. We take it to the power of D modulo N for each character in the ciphertext. Or, yeah, for each number in the ciphertext in this case. This now turns these, this now turns these numbers down here into ASCII code numbers again. And then all we have to do to get the actual message is we need to say message equals join on a string here, just on an empty string, join the character function, which is the opposite of the ordinal function, of the ord function, for each character in the encoded message. And then we can print that decrypted message. There you go. Hello world. So you can see what's happening here is basically we have these two primes. These two are prime numbers. Multiply them and you get this number. Multiply this -1 times this -1 and you get phi of n. And then basically find a number E which is co-prime to phi of n, in this case, this one here, and then find the respective multiplicative inverse D, this one here, that is congruent 1 modulo n, modulo phi of n, sorry, and then just take the message, or in this case, each character of the message, and take it to the power of public key modulo n to get this here, and then we can just decrypt it back using the private key. This is RSA explained from scratch and implemented from scratch. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Let me know specifically if you like these more theory-based videos where I show you something from scratch, not just a quick library fix or hack in Python, but something that's actually based in theory with the mathematics behind it and then how to implement it. Let me know if you like these sorts of videos. If enough people like the video, comment the video. If enough people look at the video, I will make more of those videos. Otherwise, I'm going to go back to more casual content. So let me know in the comment section down below. And as always, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.